the gradually varied flow. So we will continue with the online lectures for this hydraulics course and open channel flow that we have studied so far before the midterm. We will continue with that. So the different types of flow that we have studied, the criteria, the flow depth, if we consider with respect to time and space. So we already know that open channel flow can be classified as steady flow. So in steady flow, you can see that the depth of water, it is constant with respect to time. It is not changing. Partial y by partial t is equal to 0. So the steady flow, and if the depth is changing with respect to time, then we have unsteady flow. Now, all the problems that we discuss in this chapter are essentially steady flow problems. So it means that the depth, the discharge, these are not going to change with respect to time. If we base the classification on space, that is with respect to distance, so then the open channel flow can be classified as uniform flow. You can see here that the depth is constant with respect to time. So it means the change in depth with respect to x, So that is equal to 0. If the depth is changing with respect to x, then we call it as non-uniform flow, or commonly we call in open channel hydraulics as varied flow. Now the flow is steady, and then it can be uniform flow and varied flow. So the uniform flow we have already covered so far. Now this varied flow, when the depth is changing with respect to x, this can be further classified into gradually varied flow and rapidly varied flow. So in this lecture and coming lecture, we will cover these two topics. So this gradually varied flow and rapidly varied flow, these are relatively defined, that in gradually varied flow, the changes occur gradually over a long distance, and as the name here, rapidly varied flow means that the change in depth, that will occur abruptly over a short distance. So these are the relative definitions. Now this unsteady flow that we have, the depth is changing with respect to time, this can be further classified as uniform flow. That is, the depth is not changing with respect to time. This here, it is changing with respect to time, but this depth is not changing with respect to x. So we have unsteady uniform flow. So this is rare in practice. Clear? So we have varied flow where the depth is changing with respect to time, and also the depth is changing with respect to x. So this is unsteady varied flow. Clear? And then it can be gradually varied flow and rapidly varied flow. So as I said before, that the syllabus for this course only cover the steady flows and can be uniform and non-uniform. So that's why we will cover in today's lecture the steady non-uniform flow problems. Now, obstructions cause the flow depth to vary. When we have a flow in open channel, so it will try to flow with one depth. If the flow conditions, the channel cross sections, they do not change, so essentially what will happen is that we will observe the flow in open channel as uniform flow. But because in the flow there can be obstructions, and obstructions in the form that, for example, you can see here in this figure that we have, let's say, this bottom of the channel at one slope, but here the ground surface changes, and you can see here that the ground surface is now at this elevation or at this slope. So definitely we have to provide here a drop structure. So similarly, for example, on rivers, we have to construct barrages, dams, weirs, and other hydraulic structures. So essentially what we are doing is that we are bringing changes in the flow conditions. And generally we say that obstructions cause the flow depth to vary. So it means that the flow will continue to be uniform flow as long as there are no changes. Just like we studied in pipe flow, that when we have a laminar flow or we have a turbulent flow, so the velocity profile will continue to be fully established. But when there is a change coming, just like we studied in fluid mechanics 2 course, that for example, if we have a valve or we have a bend in the pipe, so then the velocity profile will be changed due to the change in conditions of the flow. But after that, it will try to establish the fully established velocity profile. Same is the case in open channels. We assume that the flow will occur as a uniform flow, but because there are changes in the flow conditions due to different reasons, so that's why the flow become non-uniform flow. So this is the reason why we have varied flow. Why the depth varies? So essentially obstructions, they cause the flow depth to vary. So now that we have variation in the depth, so no longer we have uniform flows. So the theory that we have discussed so far, that we have to modify to be applicable to varied flow problems. So the depth varies, obstructions cause them to vary. This is the main reason. You can see here that let's say we have one canal, but then the natural surface level that changes, or then we have to provide this hydraulic drop for different reasons. So in this case, the flow will essentially be gradually varied flow or rapidly varied flow. So accordingly, we have to analyze the problem. Before we study how we will analyze the gradually varied flow problems, first we define that we have rapidly varied flow. It occurs over a short distance near the obstacle. So relatively we define them that, as the name indicates, rapidly varied flow. It means that there will be depth in the water surface, depth of the flow that will be rapid, abruptly, and it will be over a short distance. When the depth changes gradually over larger distances, then we say that this is gradually varied flow. So we have two types of these flows: gradually varied flow and rapidly varied flow. So we will cover both of them in detail. You can see here in this figure that we have uniform flow which will occur, and if this channel continues to be like this, if there is no change, you see the flow will continue to be uniform flow. But because of different reasons, the flow situation changes. So that's why we encounter the flow to be gradually varied flow and rapidly varied flow and so on. So now essentially we should learn how we will analyze the open channel flows when we have varied conditions for the depth. So now we know that we have uniform flow. What is the reason for that? And what are the different types of flows that can occur with changing depth? So in this figure again, you can see here that a gate is provided here. This is a gate to release a controlled supply of water, and these are all practical applications. Clear? So you can see here that just downstream of this gate, we are assuming that the depth varies abruptly. So this can be a rapidly varied flow. Then in the channel, a uniform flow will establish. But you can see here that at the downstream, we have another hydraulic structure. This can be in the form of a weir, notch. So you can see here that we have the damming action. The water level rises upstream. And in this situation, you can see that there is a break in the water surface, which is shown by this curved or zigzag line. So again, we can encounter the rapidly varied flow. Now downstream of this, we have this drop structure. And also you can see that the slope is changing. So when the slope changes, so you can see here again, the depth cannot be constant at all sections. So these examples clearly indicate then when flow occurs in open channels. So according to the conditions, it can be uniform flow for certain reaches of the channel, certain sections of the channel, while for other, for example, near the hydraulic structure or near any type of obstacle or change in slope, then the conditions can change from uniform flow to varied flow. So now that we encountered the varied flow problems practically, now we need to learn how to analyze these type of problems. In case of uniform flow, we already studied that dy by dx is equal to 0. This y is the depth of flow and x is the distance along the flow. So it means that the depth does not change with respect to x. So that's why dy by dx is 0 when we have uniform flow conditions. Strictly uniform flow conditions are not possible practically because of the flow conditions. We have natural channels, even in artificial channels. So it's very difficult practically, strict sense. It's very difficult to maintain uniform flow that the depth will be the same at all sections. But this is the assumption that is made that we analyze the flow problem. So that's why the uniform flow conditions are more accurately applied for prismatic channels, clear? For artificial channels. Whereas for natural channels where the conditions can change from point to point, place to place. So that's why it's very difficult to maintain the uniform flow conditions. When we have the rapidly varied flow, so in the rapidly varied flow, you see here that the depth is changing with respect to x. And if we compare this with the gradually varied flow, so you can see here that the change in depth with respect to distance is very small. It is changing. It is not equal to 0. For uniform flow, it is 0, but it is very small. When we have this condition satisfied, we can classify the varied flow as gradually varied flow. But as the depth change in depth increases, then you can see here that for rapidly varied flow, dy by dx is approximately 1. Now, in today's lecture, we will cover the gradually varied flow problems. So, why we need to study the gradually varied flow? You can see here that in this figure, we have a channel or a river or a stream. So the water will flow with normal depth. And we defined earlier that what is normal depth? It is the depth corresponding to the normal flow. And what is the normal flow? That is the uniform flow. Clear? So if we do not have any obstruction, you can see that this water will continue to flow with the normal depth. It will continue to flow with the normal depth here. You see this dash line which is shown here. So this water will continue to flow like this. Since now that we have constructed a hydraulic structure, this is in the form of a dam, we can call it as a dam. And this we do, clear? So what will happen is that the dam will store the water behind. And this artificial lake is created behind the dam, the upstream side, we call it as the reservoir. So what will happen is that because of this hydraulic structure, the water level has increased. You can see here initially the water level is this, but now because of the dam, this water level has increased here up to this level. And this is not at a single point. You can see here that you see in the direction of flow, the depth increases. And the effect travels upstream. You can see here. And you see that up to 20 kilometer, you can see extended level of water ponded behind the dam. And this curve which results here, the top surface, this curve, you can see here that this curve is which forms is a result of impounding this water here, this one. So this extension of this backwater curve is up to 30 kilometer upstream. It means that when we have constructed the dam, so the effect of this curve, which we call it as the backwater curve. You see here, because the water is on the back of this dam, so the curve which is generated as a result of increasing the depth of water, that is the backwater curve. So the effect of the backwater curve means that the increase in this depth upstream, it has traveled 30 kilometers. This is not a short distance. Why we are interested to know about this? Because you see here that now the channel, the water flows in this channel at this depth here. But because of the dam, the water level has increased. So what will be the problem? If this channel does not have sufficient capacity to carry the water, it will be overflowed. For example, we have this channel here and the water flows in the channel. This is now for uniform flow condition. We have designed this channel. But now as a result of this dam, what will happen? The water level will rise. So if this channel has no capacity, what will happen? This water will overflow its banks. It will overflow the sides. And what will happen? That on this side, the communities, and on this side of the communities, they will be flooded. So why it is important? This effect can be important for river engineers who wish to ensure that a river's embankments are high enough to contain flows, and for landowners along a river whose land may be flooded by the dam construction. So what will happen? We have to ensure that the river embankments are high enough to contain these flows. And for landowners along the river, those people who are living along the river, whose land may be flooded because of this dam construction. And this actually happened. You see in the case of the Tarbela Dam, which is the largest earth and rockfill dam in the world, when we constructed this dam, behind the dam we have large reservoir and the water level increased. So several villages, the people, they have to be relocated to other areas. So essentially this backwater curve, which results because of the construction of the dam, this is essentially a problem of gradually varied flow. So this shows the importance of why we need to study the gradually varied flow topic. Now we know that this gradually varied flow is an important topic. Now we need to see that how we develop the basic theory and then how we analyze the gradually varied flow problems. So first we discuss the energy equation for gradually varied flow. This is the topic in your textbook. Now the energy equation, the same three forms of energy that we consider, how we can write down this when we consider the gradually varied flow problem. This is what we are going to see in this topic. So we have the same situation. This figure, we are familiar with this figure. We have this H is the total energy, and the three forms of energy that we consider, these are the Z, that is the elevation head or potential head, datum head, with respect to arbitrary datum. Clear? We have the depth of flow in the channel, and because the water is flowing with a velocity v, so it has the kinetic energy which is given by alpha times v square by 2g. Because this velocity is not constant over the cross section as we studied, so that's why we need to apply the correction to the velocity head, and that is given in this alpha, which is the kinetic energy correction factor. And in fact you calculated in the midterm exam also as a exercise. So we have the same three forms of energy on section 2. We consider section 1 and we consider section 2. Now in this case, these conditions are changing. Clear? So it means that the depth is changing because now we are considering varied flow, no longer uniform flow where the depth and velocity will be the same at all sections. So this E is the specific energy, and this E is just the sum of the depth of flow plus the velocity head, as we studied in detail before the midterm. So we have the three types of slopes that we consider. We have the bed slope, which is denoted by S naught. Then we have the slope of the water surface, and we know that in case of open channel flow, the water surface is the hydraulic grade line. So that is denoted by SW. And then we have the total energy line or the energy line, and the slope of the energy line, that is denoted by S. HF is the energy loss due to friction. Now between the two sections, L is the distance along the bed of the channel. Clear? And delta X is the horizontal distance between the two sections. So as we studied earlier, that in case of open channel flows, this theta is very small. The slope which we consider for open channel, this theta is very small. So because this theta is very small, we consider this L is approximately equal to, approximately is not exactly, approximately equal to delta X. Now, how to write down the energy equation for gradually varied flow? One thing is that for uniform flow, remember now this is important. For uniform flow, when we have uniform flow, remember for uniform flow, the three types of slopes, they are the same. For uniform flows, we can write down S naught is equal to SW is equal to S, where S is the slope of the energy line. These three were equal. That's why in the Manning's formula and in the Chazy formula, we put this S is equal to S naught. And that's why the slope of the bed of the channel, that is commonly used in the formulas. But now that we have non-uniform flows, now we are studying non-uniform flows or varied flows, non-uniform flows, or commonly we say varied flow. Commonly we say varied flow. As written in your textbook, you can see here this topic is from your textbook. So we commonly say in open channel hydraulics is varied flow. So in case of varied flow, remember the three slopes will not be the same. So it means that this S naught, this will not be equal to SW, and this will not be equal to S. So now with this understanding, let us try to write down the energy equation and how we will apply when we have gradually varied flow problems. So what we do is we just learn that the total energy that can be written as H, that is equal to Z plus we have Y. This is the potential energy head, because we are expressing energy per unit weight, so it is head. So we have the Z plus we have the depth of flow, Y plus we have this alpha V square by 2G, kinetic energy head. Now in these problems, remember this Z plus Y, this is the potential energy head, clear, above the arbitrary datum. And this alpha V square by 2G, this is the kinetic energy head. And this V is the mean velocity, the average velocity in the section. Now what we do is that this alpha, remember this alpha, which is the kinetic energy factor, this is higher in open channels than in pipes. You study chapter 8. It may range from 1.05 to 1.40 for open channels, clear. And in case of channel with obstruction, this alpha just upstream may be as high as 2. For obstruction, it may be 2 or even above, 2 or above. Clear? Now this energy equation that we have written, let's say this is equation number 1. So we will consider this energy equation for steady flow, of course, because all the problems that we study in this chapter are steady flow problems. Now between section 1 and 2, so we consider two sections as you saw in the previous slide. We have section 1 and we have section 2. That are delta x apart. What is the horizontal distance between that we consider? These are delta x apart, the two sections. It means the distance between the two is delta x. So now we can write down the energy equation. What will be that? That will be equal to Z1 plus we have Y1 plus alpha 1 V1 square divided by 2G. This is equal to Z2 at the second section plus Y2 plus alpha 2 into V2 square divided by 2G plus HF. We consider the head loss plus we have the head loss due to the friction. So let's say this is equation number 2. Now in this equation, we already know that is this Z1 minus Z2, Z1 minus Z2 divided by delta X. This is actually what? This is S0. This is S0. And this HF, this is approximately equal to S into delta X. y approximately equal to delta x. Actually it is delta L, it is not delta x, but because for small channel we consider delta x, this L here, this is L, actually it is L, but for since the slope is small, as I said, we take it as equal to delta x. So we just make this approximation that this is equal to L. So that's why this HF is equal to approximately S into delta x. And also we will assume that this alpha 1 and equal to alpha 2, this is equal to 1. This is the assumption that we are making in all the analysis in this chapter. Now if you put this equation number 2, this will become y1 plus we have v1 square divided by 2g is equal to y2 plus v2 square divided by 2g plus, now this z1 minus z2 I can write down s naught times delta x, and we have s times delta x for HF. So this will become, if you simplify, this will become s minus s naught into delta x. Let's say this is equation number 3. Now the question here is that okay, you have y1, you have v1, you have y2, v2, s naught, delta x. Clear? We can consider that what should be the value of delta x between the two sections, from where this s will come. What is s? S is actually the slope of the energy line. So now what we do is that in gradually varied flow problems, this is now the energy equation that we write down between the two sections. We can make an approximate analysis of this gradually varied non-uniform flow by considering a length of stream to consist of a number of successive reaches in each of which uniform flow occurs. What will happen is that when we have this type of problem, this is now a gradually varied flow problem. So what we are saying is, to analyze this type of problem, we can divide this into small reaches. 1, 2, then 2 and 3, then 3 and 4, into small reaches, each of which uniform flow occurs. And then for each of this small reach, we assume that we have uniform flow conditions. So when we bring the uniform flow conditions, then essentially we can apply the Manning's formula. So the Manning's formula can be rearranged and applied to average conditions. As we studied so far, that the Manning's formula, it is for uniform flow conditions. Now we are discussing the gradually varied flow problems. So because we consider the section to be very small with this delta x, we can assume that the uniform flow occurs. So with this assumption, we can apply the Manning's formula. So that's why now what we are doing, that we are bringing the Manning's formula. So that's why we say that these are approximate analysis. So we consider the Manning's formula. You can also use the Chezy formula. So this Manning's formula that we essentially developed and applied for uniform flow conditions, we can also apply it here. what we can write down in the British gravitational units, we can write down this formula is, now we are talking about the slope of the energy line. So if you simplify that, this S, which is the slope of the energy line, this will be equal to the Manning's N. This is the Manning's roughness coefficient N with velocity V bar divided by 1.486 times the hydraulic radius. This is bar, and power of hydraulic radius, that is 2/3. And because it is the slope that we calculate, so we take it as the square. Now this is in the British gravitational system. When we consider the SI units, then we drop this factor 1.486. The rest, the formula remain the same. So this will be equal to S, and this will be equal to N times V bar divided by 1.1. This will be 1. Let me not write down 1. This will be 1. This factor will drop. Only we have the hydraulic radius. So this will be equal to this hydraulic radius. This is bar and power 2/3. This is 2/3 and this whole square. Now what we mean by V bar and RH bar, because now we are considering the average conditions, because the velocity is not the same at the two sections. So that's why this V bar, this will be equal to V1 plus V2 divided by 2. And this hydraulic radius RH bar, this will be equal to RH1. You see the depth and velocity, they are not the same at the two sections. We have varied flow and we have RH2 divided by 2. So what we are doing is that we are applying it to average conditions in each reach to provide estimate of the value of S. Clear this Manning's formula to provide estimate of the value of S. Clear? Now in this case, with this value of S here, with this value of S, with S naught and the Manning's N known, and with the depth and velocity at both ends of the reach known, we can compute this delta X. So how we can compute this delta X? This will be then equal to, from that equation, this delta X, this will be equal to Y1 plus V1 square by 2G minus Y2 plus V2 square divided by 2G, this whole divided by S minus S naught. Or this can be written as delta X. We will need this equation towards the end in the analysis. This is very important. This will be equal to E1 minus E2. This is the specific energy. Y1 plus V1 square by 2G. E1 minus E2 divided by S minus S naught. Oh, this was equation number 3. Let's say this is equation number 4. Now you can see that in this case we can estimate this delta X using this formula, and the S will be calculated from the Manning's formula, and the Manning's formula we develop for uniform flow, but this is varied flow. So that's why we say that approximate analysis is possible. Now in this case, remember that the depth ranges that we will consider, because I said that we apply this for section 1 and section 2 that are delta X apart. Next it will be another section, it will continue, and that will be section 2 and section 3 and so on. So you calculate this as delta X1, you calculate this as delta X1, then in this case from here to here this will be delta X2 and so on. Now in this case, remember that the depth ranges that we consider, for example, you consider here y1, and then we consider here y2, and then you will consider here y3 and so on. So this depth ranges, remember, for this procedure must not cross the normal or critical depth. Clear? Why it should not cross the critical depth? Because in case of critical depth, if it is going to pass, what will happen? As I told you before also, if let's say we have a supercritical flow and then it changes to subcritical flow, it will pass through the critical depth. Let's say this is the critical depth. So it will pass through the critical depth. When it passes through the critical depth, we have critical flow. And when we have critical flow, there is a break in the surface, and the conditions near the critical flow are unstable. So this condition here is then essentially an example of rapidly varied flow problem. That becomes essentially a rapidly varied flow problem. So you cannot apply the gradually varied flow theory to analyze that situation. So when we analyze the gradually varied flow problem, we have to ensure that the depth ranges that we consider should not cross the normal depth. The normal depth, if it is that is uniform flow, but it should not cross also the critical depth, because it passes the critical depth, it essentially becomes a rapidly varied flow problem. This is another topic that we are going to study, how to analyze the rapidly varied flow problems. So that's why we have to ensure that when we apply these equations for the depth ranges, the depth of water in the channel should not cross the critical depth. So how you will know that it should not cross the critical depth? For that, you will apply the Manning's formula to calculate y naught. What you will do is that you will apply the Manning's formula. We can also apply the Chezy formula, but as I said before, in this book, we will throughout follow the Manning's formula. Clear? So you will apply the Manning's formula, and from that you will calculate y naught, the normal depth. Now your depth may not be the normal depth in the channel, because now the depth is changing. This normal depth is the depth corresponding to uniform flow. And also you will calculate the critical depth. You will calculate the critical depth. And we already discussed how you will calculate the critical depth. So the critical depth you can calculate YC, either you can calculate from VC square by G, this is the critical velocity, VC square by G, or it can be given as Q square for rectangular channel, Q square divided by G power 1 by 3. This is for rectangular channel. Even if we have a non-rectangular channel, this is for rectangular channel. Clear? We already discussed. You just come back from the midterm, so I'm sure you have studied a lot. So this is for rectangular channel. You can easily calculate YC. Or if we have non-rectangular channel, we already studied for non-rectangular channel, then this you can calculate from the formula, that is the total discharge, that is applicable to rectangular channels also. Q square by G equal to A cube divided by the top width, and this whole, this is for Y is equal to YC, the critical depth. So the critical depth for non-rectangular channel you can calculate from this equation, and then you will compare the depth ranges that you consider in the problem, that you will compare against this Y0 and YC, because we have to make sure that your depth ranges should not cross YC. If it crosses YC, essentially it becomes a problem of rapidly varied flow. Then we have to develop another theory how to analyze the rapidly varied flow problems. Then it is no longer gradually varied flow. So this is important, how you write down the energy equation in case of the gradually varied flow problems. Now, before we discuss how we analyze the water surface problems or water surface profiles in gradually varied flow, as you saw here, like for example, this backwater curve. This is the backwater curve. So how you analyze this water surface? Because this will tell you that along this channel, how much the water level is increased because of the construction of this dam. Ultimately, this is what we want to find out. So before we do that, what we have to study is that one is this energy equation that we have studied, and before that we need to classify the channels, because we have mild channels, we have steep channels, we have critical channels where we have critical flow. So that's why first we need to know what are the different types of channels or what are the different types of slopes, and then once we know that, then we can develop an equation that can help us to analyze the gradually varied flow problems. So first we study classification of channels now for gradually varied flow problems. So depending on the channel slope, geometry, roughness, and discharge, open channels may be classified into 5 categories. Open channels are classified as being mild, steep, critical, horizontal, and adverse in gradually varied flow studies. So it means that we can classify the open channels into 5 different categories when we consider the gradually varied flow studies. We already know this, clear? Because the behavior will be different. That's why we need to know this classification, and then accordingly we can analyze the gradually varied flow problem. So we already know the mild channel, the steep channel, the critical. Horizontal is that when the slope is 0, and adverse channel means that when the slope is negative, means it is increasing in the direction of flow. So let us study in detail these 5 types of channels or slopes, clear? So if for a given discharge, the normal depth of channel is greater than the critical depth, the channel is said to be mild. This we already know, clear? When the normal depth is greater than the critical depth, we say that the channel is mild. The slope is mild slope. If the normal depth is less than the critical depth, the channel is steep. We already know this, we have studied so far. For a critical channel, the normal depth and the critical depth are equal. When Y0 is equal to YC, then we say that we have critical flow. So that is the critical channel. And the slope of the channel, that will be the critical slope. If the bottom slope of a channel is 0, the channel is called horizontal channel. It means that in this case, what will happen? S0, that will be equal to 0. We have horizontal channel. If A channel is said to have an adverse slope. What will be called the adverse slope? If the channel bottom rises in the flow direction. So in this case, we say that S naught is negative. S naught is negative. Now these 5 types of channels we need to understand. Because we have gradually varied flow and we have these 5 types of possible channels, we need to understand, because when the flow occurs, the behavior will be different. So when we analyze the problem, we need to understand these 5 types of channels. Clear? Now in this case, let us continue with this discussion. So for mild channels, we say that Y naught is greater than YC. And when this is the situation, so subcritical flow will occur at normal depth. In steep channels, then Y naught is less than YC, the normal depth, so supercritical flow at normal depth. When we have critical channels, then Y naught is equal to YC, and we have this critical flow at normal depth. We already studied this. When we come to horizontal channels, it means that the bottom slope that is equal to 0. It cannot sustain the normal flow. I will explain. Adverse channels where S naught is less than 0 means negative, cannot sustain the normal flow. It means that these 2 channels, these are non-sustaining channels. Why? Because they cannot sustain normal flow. If you put S naught is equal to 0 or S naught is equal to negative in the Manning's formula, we cannot get the value for Y naught. That's why for these 2 channels, theoretically for these 2 channels, Y naught is not defined. Y naught is not defined. It means that these channels cannot sustain, is not defined. It means for this channel we cannot sustain Y naught. And these are known as sustaining channels, because you see we have Y naught here, we have Y naught here, we have Y naught here, but it is equal to YC. You can confirm this in the Manning's formula. Just put S naught is equal to 0 and S naught becomes is equal to negative. So you will see that theoretically Y naught is not defined. Now the question is why it is not defined, because we say that gravity is the main component for open channel flow. So if a channel is horizontal, perfectly horizontal, it cannot sustain the flow. You need a slope of the channel for flow to occur. This is what we are saying, that the gravity component is the major force, the driving component that is due to which the flow occurs in open channels. So if the channel is perfectly horizontal, of course, it cannot sustain the flow to occur. Similarly, if a channel is adverse slope, it is increasing, so a flow cannot occur. Clear? Flow cannot occur on a rising channel. So that's why we say that these 2 channels cannot sustain normal flow. But it is possible that a short segment of these channels can be encountered. For example, what we can have is that we have a steep slope, then we have a small portion of the horizontal slope, and then the water flows on another slope. So there will be a flow on this horizontal here, and then the flow can occur. Similarly, it is possible that, let's say we have a steep channel, then for a short distance we have increasing slope, and then the water can continue here. So still we can expect the water will continue to flow. But for larger segments, the flow cannot be sustained. But because we encounter them here, you see the horizontal portion or the adverse slope here for a short section of the channel, so still flow will occur. So that's why we need to study all these 5 types of slopes, channels, whatever you call it. Now in this case, this steep slope, this we will denote by letter S. When we have the critical slope, we will denote the water surface shape, whatever it occurs. You see the water surface profiles that will occur, that we will denote by capital C to differentiate from each other, just to write down these short. If we have a mild slope, this is also a relative comparison of the 5 types of slopes. If we have a mild slope, so that we will designate with M. When we have the horizontal slope, we will designate this with H. And when we have adverse slope increasing in the direction of flow, it means S naught is negative, that we will denote by this A. So these are the relative comparison. You can see that the different types of the slopes that can exist for the open channel flow. Now you see that we already know that for mild slope, S naught is less than SC. When we have steep slope, S naught is greater than SC, where SC is the critical slope. When we have critical slope, you can see here S naught is equal to SC. For horizontal slope, S naught is 0. And for adverse slope, S naught is negative. So this is a relative comparison where you can see and get the idea that how we can define these 5 types of slopes for the open channel flow. So now when flow occurs over these channels, you cannot expect the same behavior. That's why we need to first understand these 5 types of slopes that exist for open channels. Now the channel bottom and the critical depth line as well as the normal depth line, these 3 together, they divide the channel into 3 types. We will call them types. We follow our textbook, we will call them as types. If you study other books, they will call them as zones or regions, meaning the same in the vertical dimension. So what we can do is that when we consider the channel bottom, we consider the critical depth line and we consider the normal depth line, we can divide the flow in the channel into 3 types or 3 zones or 3 regions in the vertical dimension. What are these 3 zones? If the depth of water is above the 2, which 2? One is the normal depth and one is the critical depth. If the depth is in the channel is here y, if this is the depth of flow, then we will say that it is type 1, zone 1 or region 1 flow. If this is y, if the depth of flow in the channel is between the 2, now we are not saying y naught should be above or yc should be above. No. Between the 2, whatever. Between the 2, if the flow depth occurs between the 2, we will say that it is type 2 or zone 2 or region 2. And if the depth of the flow is below the 2, means the normal depth and the critical depth, then we will say that it is type 3 or zone 3 or region 3. So what I'm saying is that type 1, when water depth is above the normal depth and the critical depth. When we analyze the problem and we find that y is more than the normal depth, which comes from the Manning's formula or the Chezy formula, and the critical depth that we already discussed, it is above that, we will say it is type 1 flow. If the depth is between the two, the normal depth and the critical depth, we will say it is type 2 flow. Now we are not saying which one above, which one below. No, this we are not saying. We are just saying above the two, between the two, and below the two. So that will be type 3. If the water depth in the channel is below the two depths, normal depth and critical depth, we will calculate in the problem these three. The y is the depth at which the flow occurs. It may not be y naught because we do not have uniform flow. Y naught is that when we have uniform flow. So the flow may not be uniform, as we are discussing now, varied flow. So but we can calculate that what should be the depth at which the uniform flow will occur. And the critical depth you can calculate. So you can compare the three. If the depth in the channel of open channel flow, the depth of water is above the 2, it is type 1 flow. Now which one above, y naught is above yc or yc is above y naught, this we are not saying. If the depth is above the 2, type 1, between the 2, type 2, below the 2, type 3. Let me show you another figure here. You can see that we have mild reach. It means we have mild slope. So when y is above the 2, this is the normal depth and this is the critical depth. Above the 2, type 1, zone 1, region 1, whatever you call. Between the 2, type 2, region 2, zone 2. Below the 2, if the depth is here, let's say this is the depth. So it is below the 2, this is now y. It is below the 2, this is type 3, zone 3, region 3. Even if we have the steep reach, now you see yc is above y naught. Still, if a depth is here, this is type 1. If a depth is between the two, it is type 2. If a depth is here, this is type 3. So it means that we are not saying that it is between what? Yc should be above y naught or y naught should be above yc. No, we are just saying here relatively, remember, if the depth is above the 2, it is type 1. If it is between the 2, it is type 2. If it is below the 2, it is type 3. So now what we are saying here, essentially we study 5 types of slopes. We study 5 types of slopes in the channel. So how many slopes that we studied now for our understanding? 5 types. Mild slope, steep slope, critical slope, horizontal slope, adverse slope. So now we have studied 5 types of slopes. And for each slope, you can see here mild slope or steep slope. For each slope, 3 zones exist. We will say types as per our textbook. In our textbook, they say types. So how many types exist? 3. So it means that how many different types of water flows can occur? Because the surface can be here, the water surface can be here, the water surface can be here. So 3 possibilities for mild slope. The surface can be here, the surface can be here, the surface of water can be here. 3 possibilities for steep. So it means that we can have 5 multiplied by 3. It means that 15, so far 15 possible water surface flow can occur, or water surface profile rather, I will say. 15 are now possible. Clear? Now the next question is that we can have now 15 types of flow conditions that we have to analyze as the gradually varied flow problem now. Now the next question is that all these 15 water surface profile possible? Now the question is no, not all of them. Means that not all possible. Not all possible practically. Not all possible. Why? Let us answer this question. Because when we consider the critical slope, so for critical slope, when we have critical slope, what will happen that y naught is equal to yc. Y naught is equal to yc. So when y naught is equal to yc, it means there is no zone 2. It means no type 2 or zone 2 or region 2. No zone 2. So it means that this zone 2 is not possible for critical slope because yc is equal to y naught. So it means that out of 15, this 2 is not possible for critical slope zone 2. So now we are left with 14. Now when we consider horizontal slope, and when we consider adverse slope that we just studied, adverse slope. Now we studied that for these two types of a slope, they cannot sustain y naught. There is no y naught defined for horizontal slope and adverse slope. So it means there is no y naught for these two type of slopes. So it means that the depth can be above the critical depth, it is possible, and the depth can be below the critical depth. You understand? The depth can be above the critical depth and it can be below the critical depth. So it means that the y naught for these two slopes, y naught is what? Y naught is, let me write down y naught. Actually it is infinity. Y naught that we define for these two, this y naught, the normal depth, that is infinity. Now for zone 1 to occur, it says that the depth should be above the 2. The depth should be above the normal depth and the critical depth. That is zone 1 or type 1 or region 1. So it means that for these two types of slopes, we have no zone 1. We have no zone 1, type 1, region 1, whatever you call. No zone 1 occurs. So now zone 1 cannot occur for horizontal slope, zone 1 cannot occur for adverse slope, and zone 2 cannot occur for critical slope. So that's why out of this 15 minus 3, we have 12 possible water surface profiles. 12 possible water surface profiles. So now in the problem, in the questions, 12 different types of possible water surface profiles can occur, and we need to analyze them. So how to do it, we will continue after the break.